Okay. So, in the last class we saw the definition of constraint satisfaction problems, and we made this observation that solving a CSP basically allows cooperation between two kinds of algorithms, one which does search over possible assignments and the other which does some kind of reasoning which we will call as propagation. So, we have this notion of consistency, and we have this notion of I consistency. So, we say that a CSP or a network is I consistent if every consistent assignment to I minus 1 variables can be extended to I variables, which means that if you have found values for I minus 1 variables, any I minus 1 variables, then you can always take any ith variable, any next variable and extend, find a consistent value for that. So, of course, not all networks will be I consistent, but the general effort in reasoning is to enforce consistency in some manner essentially. So, we can start with the very simplest notion of consistency, which is called node consistency or one consistency. So, when you say one consistency, then we use the term node. So, it basically means that you take any variable and you will find one value which is consistent. What do we mean by consistent with one variable? That if there happens to be a constraint over only that variable, a unary constraint, then all the variables satisfy that thing. So, we can enforce node consistency by simply saying that if there is some value which does not satisfy a constraint, remove it from the domain. So, in general, node consistency and that is one consistency and two consistency will prune domains essentially. So, two consistency is what we will look at. It is called arc consistency. And what two consistency says, that you take a assign a value to any variable which is node consistent, which means that value satisfies any unary constraint that there might be. You take any other variable and you will be able to find a value for that variable which is so that the two values for the first variable and the second variable are together consistent essentially. So, to talk about arc consistency, it is often useful to draw what we call as a matching diagram. And the matching diagram basically does something like this, that it creates a domain for each variable. So, this is x1 and this is x2, and then you have variables inside these domains. So, these are the values that this variable can take, and an edge represents the fact that this value, let us call it A1 and this value let us call it B1, belongs to the relation essentially. So, basically it is a depiction of the relation essentially. So, whatever the relation is, something like this. So, such a diagram is called a matching diagram, and what we want to do in arc consistency over these two variables is to keep only those values in a domain for which there is a corresponding value in the other domain. So, for example, we do not want to keep this value because there is no matching value in the other domain. We do not want to keep this value, we do not want to keep this value. So, to implement this, we have a simple procedure called revise, and this is kind of standard name for it, dx dy r x y. It takes, so we say that we are going to prune the values of dx to only those values which have a value corresponding value for this r x y. So, if this is x and that is y, you can prune this essentially. So, for each a belonging to dx, if there is no b belonging to dy, remove a from dx. Very simple procedure which looks at each value. So, this is a procedure which is only pruning the domain dx. So, it looks for each value, if this is x and that is y, then it looks at each value of x, and if there is no value in y, if there is no b belong to dy, I should have added such that a b belongs to r x y. In other words, if we have a binary constraint over x and y, then every value of x should have a matching value in y, and this procedure revise is pruning this domain x, domain of x here essentially. So, it looks at all these values, and for every value where there is no matching value on the other side, this one has two values. So, this one has no value. So, it will remove this from the domain, it will keep this, it will keep this, and it will remove this. So, it will remove two values and keep one essentially. So, the process of doing R consistency is basically doing this repeatedly, so that all pairs of variables are consistent essentially. So, the simplest algorithm for doing that is called EC1, stands for R consistency 1, and it does basically the following: that for each pair x y such that r x y is a domain, r x y is a constraint, call revise dx dy r x y, and call revise in both directions dy dx r x y. So, we will assume that r x y contains the relation between them. So, instead of writing r by x, I am just writing r x y usually. So, for each pair x y of variables, we want to do this, which means if I have 3 variables, let us say this one, and let us say I have something like this. So, this is x, y and z. So, I have three variables, 2 relations between x and y and z, and I want to make this network R consistent, which means that every assignment to one of these variables can be extended to an assignment of 2 variables. Notice that in the constraint network diagram that we had drawn earlier, we would have drawn this like this. We would have said this is y, this is z, and this is x. So, there is a difference between these two. This is called the network, constraint network. It is basically a constraint graph which says which variable is constrained by which variable, and we are talking about binary constraints. So, we have only edges. otherwise you would have hyper edges. The constraint graph basically identifies which variables are related to each other. The matching diagram tells you which values of variables are participating in those constraints. When we say something like this, that this is the constraint graph. So, if you remember this map coloring example that we saw, we said that if this is, if the domains of all three are red, blue, and if this is not equal to this and this is not equal to this, that is a constraint given to us. Implicitly we have a constraint between this and this, which says that anything is allowed. So, RB is allowed, R is allowed, BB is allowed, and BR is allowed. If we have not specified, a constraint, that means implicitly it is a universal relation, which means anything is allowed to anything, which means what, that our backtracking algorithm said that if you first want to give a value for x and if you want to give a value for z, it is not putting any constraint on you, which means you can choose, if you choose R for x, you can choose B for z, or you can choose R for z, it does not care, because it does not know any constraint essentially. So, there is a universal relation sitting out there essentially, but of course, it is not explicit, it is implicit. So, it does not participate in the matching diagram here, and it does not participate in this Rxy. So, when we say Rxy is a constraint, we mean it is an explicit constraint mentioned in the CSP essentially. So, before I come back to this, we have a notion of 3 consistency, which is known as path consistency. Remember the notion of I consistency, which is a generic notion. 3 consistency says that any pair of values which are consistent can be extended to a third value. So, if I choose 2 values for this, I should be able to extend it to a third value. So, if I choose red for this and blue for this, I can extend it to blue for this, right. If I choose blue for this and red for this, I can choose blue for that. But if I choose these 2 values first, if I choose red for this and red for this, then I can extend this to blue for this variable y. But if I were to choose red for x and blue for z, then I cannot extend it to y. So, this network as given to us is not 3 consistent or is not path consistent. What path consistency would do would to prune this relation in this example. So, what would it do, that it will say that okay, you choose red for this and blue for this and you cannot extend it to a value. So, this red blue must be removed from this relation. You choose blue for this and red for this and you cannot extend it to a value. So, you must prune this from the relation. So, enforcing path consistency prunes relations. The moment you are pruning a universal relation, you are making it explicit. So, in fact, it adds a new relation. So, when you do path consistency, you get a new network which looks like this. It adds a relation in some sense, in the sense that earlier it was a universal relation, but now it is not a universal relation. So, you have to explicitly represent it, which means x is now related to z. So, these 2 are not equal to, but this one is equal to. So, we have a new network. So, the general idea of enforcing consistency is to limit the choices available to a search algorithm to only those which are likely to participate in solutions. But since an n variable problem will have n variables, so to really achieve full consistency, you would have to achieve n consistency, which of course is, you can take it from me, is a hard task. So, which is why we do not often do it. So, very often algorithms will do achieve some degree of consistency, either node consistency or path consistency, R consistency or path consistency, or some higher order consistency, depending on how complex the problem is, and then leave the rest to search and leave the rest to those other kinds of things that we just briefly mentioned in the passing, like dependency directed backtracking or look ahead in search. So, there are various tools in the armory of a CSP solver. Consistency enforcement is one of those tools essentially, which is what we are trying to look at today. So, coming back to arc consistency, I want to make this network arc consistent, which means if I choose any value in any variable, I should be allowed to by the consistency given to me choose a value for the next variable. So, obviously as we saw when we call, so what will you do, we will call revise with x and y, with y and x, with x and z, with z and x, with y and z and z and y. So, at least 6 calls to revise we will have to make. Remember, revise is a directional call, it prunes only the domain of the first one, that if for each x a in dx, if there is no corresponding value in y, remove this a from dx, that is what revise does for this. So, we have to make at least 6 calls to revise. Are those 6 calls enough? This is a question I want to ask you. If I say revise xy, revise yx, revise xz, revise zx, revise yz, revise zy, am I done? Do I get a network which is arc consistent? Let us try it out on this. So, let us call revise xy first, which means we are going to throw this away and we are going to throw this away from this essentially. Then let us call revise yx, which means we are going to throw this away from the domain of y essentially. So, let me actually circle it so that and cross it, so that we know that those things are not there essentially. Then let us call xz. Xz we do not have a constraint at all. The constraints given to us is this constraint diagram, which does not say anything about xz, which means it is a universal relation, which means there is no constraint on choosing any value from there. So, this revise call will not do anything, but we have a constraint between y and z. So, let us try that. For this we have this value, for this we do not have this value. So, we have to delete this. For this we have this value, for this we have this value, anyway this is not there. For this we do not have this value, so we have to delete this. So, this is gone. Now, but you see what has happened, the moment I have deleted this value, well this still has one left here, but this the moment I have deleted this value, this one does not have a matching value here. So, I did something for revise xy, but now when I did revise yz, I deleted a value of y and this value of x does not have anything left. So, at least one more call to revise I will have to make essentially. So, if you do this, then this one has this one does not have this. So, this goes away, this one does not have this. So, this goes away, this one has this, so this goes away. So, it is almost arc consistent except for this value here, this value does not have a corresponding value here, this value has this value here and then this value has that value there, this value has this value here and that has that, but this one does not have a value here. So, I must make another call to xy. So, which means I must put this into a loop, and what is the safest thing to do? Until no more changes, okay. Until no domain changes, I will keep doing this revise, all these revises, these things. At the very outset you can see calling revise xz does not really make a sense, but of course we are not calling revise xz, because the condition says for each pair xy such that rxy is a constraint. So, rxz is not a constraint, so it is okay. We will make calls to revise xy, yx, yz and zy repeatedly till we come to a condition where no domain has changed, because then we are sure that it is arc consistent. So, is this algorithm clear? Is it nice? Is it a good algorithm? The answer is no, because it can be argued that the number of calls to revise that you make is actually very large, that in the worst case in every cycle you will remove only one value from one domain. In the worst case you can construct a network like that. So, that in one cycle, which means a complete set of revise calls, you will remove only one value from one domain, and in the next cycle you will remove one value from one domain. So, if there are n domains and let us say all of them are connected and each of them has k values, then you will make n into k cycles, which is obviously not an efficient thing to do. And the reason for that is that why should we do this brute force call to all combinations of revise? Now, if you look at what is happening here, what we should have done is the following, that when we made this revise y z call and then we deleted this value from the domain of y, we should have said y has changed. So, therefore, any constraint participating in a relation in which y is there, look at that relation again, because y has changed, any x y is participating in this thing. So, look at that relation again essentially. So, which means when we delete a value from a domain, then we should add for future revise calls only those relations which are participating with that variable essentially. So, that actually leads us to an algorithm which I will not describe in any more detail here, which is called EC3, which was described by Freuder, who is considered by many to be in some sense the big boss of constraint satisfaction. And if you want to meet him, you can go to University of Cork in Ireland, where there is a big constraint center, and it is probably the place with the largest population of constraint researchers essentially. So, that algorithm for some reason is called AC3. There is no, there is a AC2 is missing or lost essentially, but this AC3 algorithm, what so I will just briefly describe again what it does is that initially it maintains a queue of all possible revise calls, but then it removes elements from the queues when it makes a call. It adds to the queue only if it deems it necessary that I need to check this relation again essentially, which means if I have deleted something from y, then I should check this revise x y call again, make this, at least this I must do again. If I delete something from in this case it is only y. So, if I delete something from y in a call from y to x, then I must make a revise call to z y again essentially. So, only if there is a danger of having lost some matching value, I will make a call to revise again. So, I will put that particular revise call in the queue, which means only where changes are happening, this constraint will be propagated in that sense. That is why we call this constraint propagation. And yet another algorithm, which of course we will not discuss, called AC4, does not even make generic calls to revise again. It says this value has changed in this thing. So, if this value was a matching value for some other, so let us say this value was a matching value for this value in x, let me go and check if x still has a matching value or not, otherwise I will remove x from that. So, it does not even make this revise x y call again, it only looks at this particular value to see if there is a corresponding matching value left, because it could have had another value, in which case of course you do not have to delete it, but simply because it does not have any value remaining after this has been deleted, this should be deleted. So, that is a still finer level detail algorithm AC4, and obviously the complexity decreases as you go from here to here, representation increases, you have to represent more things essentially. So, I want to talk about one particular constraint satisfaction problem, where an algorithm which is claimed to be somewhere between AC1 and AC2 or close to what would have been AC2 if it had been described is used, and this is a famous problem known as Huffman close labeling. And there is a well known algorithm called Wald's algorithm, which is somewhere like AC2 more or less, so it is not officially called like that. So, let me first describe the problem. The problem is for scene labeling, and when we say scene labeling, we mean that we have a line drawing available to us and you must label it essentially. So, for example, you have a figure like this, so we will look at a variation which talks of simple figures, though Wald's algorithm actually applies to more complex figures. The simple figures that we will talk about are trihedral, which have 3 faces. So, each vertex has 3 faces and the faces are planar. So, any object which is made up of planes where the surfaces are planar and where every edge, every vertex is made up of exactly 3 edges. So, all these vertices qualify. So, this has 3 edges, 3 edges and 3 faces coming to meet there. This vertex has 1, 2 and 3 faces. So, every vertex is made up of 3 faces. Such objects are called trihedral objects, and certain objects, for example, if I were to draw something like this, if you can imagine this, it is overlapping with this. So, let me rub off that a bit. Some object like this, would not be a trihedral object, even if it were to be an object, I think. So, anyway, this is not the kind of object we are dealing with, and we are interested in these kind of objects. Now, it is a labeling problem, which means you have to label every edge, and the labels are as follows. Plus label stands for convex edge. Remember, we are talking about an edge. So, by convex we mean that the matter or material is inside. In some sense, I would label this edge as plus, because it is a convex edge as when seen from outside. Minus edge is concave, and I would label this and this edge, for example, as minus, because it is made up of a concave. So, corner of a room between the walls and the roof, for example, these are all concave edges essentially. And various books use different, some people use the notion fold and blade, but we will use the notion of arrow, either pointing this way or that way. We will distinguish between them, but the general idea is matter on right side. What do you mean by right side? That if you are following the direction of the arrow, the matter is on the right side and the other side is blank or air or space or whatever. So, if I were to look at this figure, matter is this side. So, I must label it like this, and like this and so on. So, this Huffman closed labeling task is to label a line drawing with these 4 kind of labels. In a more general case, there are other kinds of labels that you use. For example, if you have shadows and if you have cracks in objects, or if you have more than 3 edges, 3 faces meeting at a vertex, all kinds of edges can be there, and there could be other kinds of labels. But for this very simple class of objects, which is trihedral objects, which are made up of planar surfaces where each vertex is made up of 3 faces, there are these 4 kind of edges you can use to label an object. The task is to find these labels essentially. Now, the space for this problem, so you can see, is that each edge can be labeled in 4 ways essentially, and we are interested in vertices. So, when we look at a line drawing like this, we can distinguish between 4 kinds of vertices. One which we call as a y vertex, which looks like this, which is made up of 3 vertices which are looking something like this. One we sometimes call as a w vertex, which looks like this. One we call as a t vertex, which looks like this. So, this is 3 edges. Okay. So, this is a vertex, but the viewpoint is like this. So, if you were to see it from here exactly, it would look like a t essentially, and the 4 is an L vertex where you can't see the 3rd edge, which is coming to that essentially. So, for a trihedral object, these are the only 4 kinds of vertices that we can see, and we are assuming here that these are generic views, and these vertices, and it is not as if we have 2 objects and somehow by placement of 2 objects it looks like it is a straight line. We avoid such views essentially, where the little bit of a line change of camera, if you want to call it, will change the view. So, we assume that these are kind of generic views essentially, and the task is to label line drawing like this. So, if you go back to this original drawing, you want to find the set of labels for this. Now, any vertex with 3 edges coming to it, in principle can be labeled in 4 into 4 into 4, 64 ways. So, 64 plus 64 plus 64 plus 16. But because these objects are trihedral, we know that they can be labeled in less than 4 ways. So, let me take this example, this W vertex, it can be labeled as, so I will label it from left to right. It can be labeled, this can be minus, and this can be plus, and this can be plus. As you can see here, minus, plus and plus, that is one possibility, or it can be matter on. So, let me just label it, it can be like this, as you can see here, this is plus, this is like this, this is like this, or it can be plus, minus, minus. Do we have an example? We have one here, this is plus, this is minus, and this is minus. Now, it turns out that for this W kind of vertex, these are the only 3 physically possible set of labels. So, from 64 we have brought it down to 3. Can we exploit this information is the question we ask in this labeling problem, and I will leave this as an exercise. This is brought down to 6, this is brought down to 6, and this is also brought down to 6. So, there are only 6 ways of labeling these T joints and so on. So, this T can be, for example, part of a table. Okay, so, you have a table and this is a leg or something like that. So, you could see a T joint here, in which case you can imagine this will be like this will be like this, and this will be like this. This is one of the 6 ways, and there are 6 different ways you can label a T joint, and it should be an interesting exercise for you to try and find this out. So, how can we exploit this information? The one simple piece the one simple fact we should exploit is that one edge can be labeled only in one way at both the ends. So, every edge has 2 ends, it participates in every edge participates in 2 vertices. So, it must be labeled as the same in both the ways. Okay. So, for example, once I have labeled this edge as plus, it means it is plus at this end, it is also plus at this end, obviously it is the same edge essentially, it is a simple trihedral object we are talking about essentially. Once I know that this particular edge is plus here, this part is plus, I have constraints on these parts. So, I can look up my table for this out of the 6 possible relations, which of them has a plus in the middle and what are the 2 other things on the side. So, I can prune the domains of that particular those 2 edges exactly like we pruned the domains for in the crypto arithmetic puzzles. When we got some value, we pruned values for the domain essentially. So, what Wall's algorithm essentially does is that it first does a scan of this entire set of line drawings. It makes an assumption that this is a solid object, which means the outermost edges are the boundaries, which means matter lies inside them. So, it can start off by labeling this, then labeling this, then labeling this, then labeling this, and so on, and then it does propagation essentially. That once you have these outer labels, they will constrain the inner labels. So, for example, if you look at this place here, it allows only a positive label to be given here, because in the W joint we have only these 3 are possible. So, once we have fixed this variable, we can propagate this plus to here, and if this is plus, you will see that this plus 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 is one of the few combinations that is allowed essentially. So, this is the idea of propagation essentially. Once you know a value at some place, you propagate it to the next one and prune the domain for the next one, exactly like what we talked about here, revise the domain of a particular variable, and this is roughly what Wall's algorithm does essentially. So, let me give you another example where constraint satisfaction has been used as a mechanism for doing something, and this example comes from what we call as consistency based diagnosis. So, let me use one standard example which we use in this thing. Let us say we have a small device made up of 3 multipliers. So, this is M1, this is M2, this is M3. It takes 2 inputs. Let us say the inputs are fixed. So, let us say I1, I2, I3, I4, I6. It produces, each produces one output, and let us say this output is fed to an adder, and this output is fed to another adder, and we have 2 values here. There is a small device which does something, some addition, multiplication, combination. So, consistency based diagnosis is kind of also called as model based diagnosis. So, model based or consistency based diagnosis, What it says is that you construct a model of the system, and the model that we build is a constraint model. And how do we do that? We say that a multiplier is defined as follows, that if it is OK, then I will use this for an implication sign. Output of M equal to input 1 into input 2. So, I am defining a multiplier which works by saying that if the multiplier is OK, then this relation must hold, which is a constraint between these three variables of a multiplier, that O m is equal to I 1 into I 2, and so on for the others we can define. Then we can talk about connectivity. We can say that the output of M 1 is equal to input 1 of A 1. Okay, in some notation we can say this. So, we are saying essentially that this output is connected to this input, and that is expressed by this. This is also a constraint between two variables, that this value must be the same as this value. That is all we are saying. So, we describe these 3 multipliers plus 2 adders using constraints like this. These are logical constraints, in a sense it is a logical statement, this implies this essentially. We can convert it into a Boolean constraint, with this being a statement of some sort. So, we describe the whole device by saying this part tells you what the connectivity is, this part tells you what the behavior of individual component is, and between these two we have described the whole device essentially. So, now what? Now, supposing we get this input 2, input 3 here, what do we expect? We can predict that what this device will produce is 2 into 3 6 here, 2 into 3 6 here, 2 into 3 6 here, and then 6 plus 6, it should give us 12 and should give us 12 here. That is the expected output essentially. But what happens if O A2 is equal to 12 as expected? This is a real value or real constraint or observation, as some people would call it, but anyway it is a, in the CSP notation it is a constraint, and O A1 equal to 10. Now, supposing I give you this problem, what is it? It is a constraint satisfaction problem, where this is a variable, Boolean variable, it is either true or it is false, and this whole statement is also a Boolean variable, it is either true or it is false, which can be inferred from the mathematics. So, let us not get into the details here, but there is basically a set of constraints which through the description of the multipliers and the description of the adders predicts what the output should be. But the system given to us is that the inputs are these 2 3 2 3 2 3, this is a multiplier, this is a multiplier, this is a multiplier, this is an adder, this is an adder. The outputs that you are seeing is output here is 10, the output here is 12. So, what is happening? Okay. So, this approach to diagnosis, the task of diagnosis here is to identify a faulty component, and so we assume that connections are never faulty. So, this is a simplified way of looking at things, that one of these either the multipliers or the adders has become faulty. So, how do we do this? So, just as a description level we say that this is a CSP, each of these, the 3 inputs are variables, this is a constraint between those variables, 3 inputs and this multiplier. So, M1, I1, I2 and O1, 4 variables, this is the constraint between those 4 variables. If M1, if the multiplier is OK, then the output of multiplier should be equal to the product of the two inputs. Likewise for the adders and the multipliers, other multipliers. So, I have these constraints, I have the constraints that I1 equal to 2, I2 equal to and so on, and I simply say give me a solution for this CSP. What are the variables which are missing? The variables which are missing are the, so I know the input variables, I know the output variables, I do not know the intermediate variables, and I do not know whether all the devices are working or not. Okay. So, without going into the details of how this CSP is searched over, and it is quite a domain in itself, and there is a whole community which does model based diagnosis. The idea is to find a solution to this CSP, and what will be the solution look like? The solution will basically say some of these things are false essentially. For the CSP to be satisfiable, some device, some component must be faulty, some component, some statement which says this component is okay must be false, and that will be discovered in the solution, which the solution remember must contain this, that this output is 10, which means I am making a statement like 10 is equal to 6 plus 6, that is what the adder is saying. So, obviously, this is a false statement. Now, whether the fault is with the adder or whether the fault is with the two inputs, because nobody has told me that the input is 6, the input is hidden from me, it could be something else essentially. So, is this adder faulty, is this multiplier faulty, or maybe these two multipliers are faulty? It is possible that these two are faulty in such a way, or no, that these two are faulty in such a way that this is doing something and this is undoing that and producing 10, and what this is doing wrong is being reflected here. It is possible. So, diagnosis, of course, there is no clear cut answer to this question as to why are we seeing this value 10 here, but the algorithms are driven towards finding minimal diagnosis, which kind of is a Occam's razor that you must have heard of, the simplest solutions are the best, which says that all those diagnoses in which only one component is faulty are the preferred diagnosis. And then you can see that it must be either A1 or M1, and the algorithms actually find that essentially, that either A1 is not okay or M1 is not okay, and that is why we are seeing 10 there. So, what I wanted to show here was that this is another example where the problem can be posed as a CSP and solved as a CSP essentially, and this is a problem of diagnosis essentially. So, I will stop with constraint satisfaction here, because we do not have too much time left in the course, and in the remaining part of the course I want to look at knowledge representation, which is really a core of AI, and we should not finish an AI course without looking at knowledge representation and reasoning. So, the next few lectures will be focused on logic as a language for representation and reasoning essentially. Okay.